let's talk about transformers, which are very important to our power grid. You might recognize this diagram, which I used when I was in another video when I was talking about power in electrical devices and electric circuits. The idea is you have a power station, which is going to generate the electricity, and it needs to transfer that electricity at a high rate. And it's going to transfer it over a long distance using power lines to a substation, which is usually located in the city. And then from there, it's going to go to our homes and businesses. Now, as I said, it needs to transfer a lot of energy quickly. So that means a high power. And of course, this is because we're consuming a lot of electrical energy day to day. So need a high power. It's got to transfer a lot. That means you need a high current or a high voltage. But the problem is the power lines themselves have resistance. They are resistors. They will transform some of that electrical energy into thermal energy. And that depends on the current and the resistance. Now, resistance depends on the resistivity, the length, and the cross-sectional area of the wire. So you do what you can to keep the resistance as low as possible by choosing an appropriate material and making your wire sufficiently thick. But what really matters is the current. Because the current is squared, you really need the current to be as small as possible. But the problem is, if you have a small current, we still need a large power transfer. So that means a high voltage. And that's why all power lines say danger high voltage. So the question is, though, how do you get a low current and a high voltage? And that is where transformers come in. So this is your basic transformer. It's usually just a block of iron, although engineers have done some very ingenious things with transformers to improve their performance. But for our purposes, we're going with a basic transformer. It's just a block of iron. And what you do is you bring a wire in and you wind it around one side of the transformer like so. And then you do the same thing on the other side. Now, I want to mention, I said it's a block of iron, but the important thing is that it's a magnetic material. And that's why they choose iron, because iron is an excellent magnetic material. So you've wound these wires. Now, why are we winding the wires around? Why do we want them wound around the iron? Well, the idea is you bring a current in, okay, and let's say it's a DC, a direct current, and that just means that the electrons go one way all the way around the circuit, or one way in the wire. So if it's DC, it's going like this, winding around like that. So if you use DC, and if you use a constant DC, because it's a current, a magnetic field will be generated, and that magnetic field that will be carried through the iron. That's why we're using a magnetic material, so that the field travels through this material, through the iron, or I should say, so that it passes through this secondary group of coils, of loops. Now, if you're using a constant DC, then these loops are just going to see a constant flux. Nothing interesting is going to happen. Transformers work best with AC, which is alternating current. In alternating current, the individual electrons do not actually travel all the way around the circuit. They just oscillate in place, like this, go back and forth. Okay. And then so if one is oscillating, then the one next to it starts oscillating, and so on and so forth. Okay. It's kind of like longitudinal waves. So the electrons that are in these wires, they're oscillating. Okay. So that means the current is changing. So there is a current, a magnetic field is created, but because the current is changing, the magnetic field is constantly changing. That means the flux is constantly changing, and that means a current will be induced over here in the other set of coils, the other loops. Now, what this all amounts to is we're talking about a transfer of energy. Okay. So we can talk about the power that is involved. We can talk about the power in the first set of loops, which is called the primary, and the second set of loops, which is called the secondary. Now, I want to be clear. As I've drawn it, either set of loops could be the primary and the other one would be the secondary. The primary is defined by which one is bringing energy into the system. One set of loops is bringing energy into the system, into the transformer, and the other one is taking it away. And ideally, all of it is taken away by the secondary. So energy comes in via the primary, and it all leaves via the secondary. This isn't what actually happens. Transformers actually, there are some thermal losses in the transformers themselves, which can sometimes lead to a breakdown of the transformer itself. But we're going to look at the ideal case. We're not going to worry about any thermal losses. So ideally, all the power that the primary brings in, the secondary takes out. Now our formula for power here, IV, this is our general formula, so we can write this down. And we can rearrange this. Like so. We get these ratios, and these are very useful ratios. Notice that on the left side with the currents, it's the primary over the secondary, but on the other side, with the voltages, it's the secondary over the primary. Now remember that Faraday's law, let me write Faraday's law down here. Faraday's law tells us that the voltage that is induced depends on the rate of change of flux. And so you can look at these coils. These coils, the more coils you have, the more change in flux that is going to be seen. Okay, and each of these coils has the same area. And so what ends up happening is you can say, well, the change in flux through a single loop or coil is going to be the same as it is through every other one. And so it turns out that this ratio of voltages can turn into a ratio of just the number of loops. And this is important because this tells me how to actually build the transformer. It's the number of loops that actually matters and is going to get me the behavior that I want. So this ratio is extremely important. And what we see is that if the number of coils in the secondary, so for example, if this is the secondary, if the number of coils in the secondary is greater than the number of coils in the primary, this ratio is greater than 1. And that means the voltage in the secondary must be higher than the voltage in the primary. So the voltage here must be higher than the voltage here. This is known as a step-up transformer. We can step up the voltage. We can get the high voltage that we need. And at the same time, this ratio, since this one is greater than 1, this one has to be greater than 1. That means the current in the primary must be higher than the current in the secondary. So that means that going from the primary to the secondary in a step-up transformer, we're increasing the voltage and decreasing the current. We can get exactly what we need. We need a high voltage and a low current via the transformer. And so that's what happens. There are transformers here over at the power station, which they're step-up transformers. They step up the voltage and simultaneously lower the current. And so you've got high voltage power lines all the way to the substation. Then at the substation, there are usually, well, at least there can be, there can be transformers there. And these are usually step-down transformers if they are there. And so the substation will have some step-down transformers. For those, the primary will have more coils than the secondary, more loops. So this, for example, would be the primary, and this would be the secondary in a step-down. And so now this ratio is less than 1, so the ratio of the voltages is less than 1. That means the primary voltage is higher than the secondary voltage. So this voltage is lower than this one. And that also means that since this ratio has to be less than 1, that must mean that the current in the secondary is higher than the current in the primary. So this one is going to have a higher current. So the step-down transformer lowers the voltage. It steps down the voltage, but it raises the current. So we get higher currents here, and then it goes to your home. Although I should mention that often in neighborhoods, there's a transformer. In fact, there's probably many transformers where it steps down the voltage again and raises the current yet again before it does enter your home.